All right, recording is re-rolling. All right, here are the FRQs that you guys got. I'm gonna try to do them all today, but we'll see. Okay, so probably keep a little bit fast pace on these. All right, so we're start out with a 7-point question, 13 minutes. A cart on a horizontal surface attached to a spring, the other end attached to a wall. The cart initially at rest is shown in figure 1. Okay, ooh, look, it looks like they pulled out to some stretch distance plus L. Okay, and it oscillates between L and negative L. The kinetic energy is shown as a function of potential energy. That's interesting. I don't know if I've ever quite seen a graph like that, or very rarely, right? Did they say there was negligible friction? Oh yeah, friction is negligible. Great. On the graph of K versus U, kinetic energy versus potential energy. Okay. By the way, guys, are they talking about gravitational potential or spring potential? Spring potential, and only spring potential. There's no height change, but there is a spring length change. The values for x and y the values for x-intercept and y-intercept are the same. Explain why this is true using physics principles. Guys, there's a physics principle. It's 3 words. It's what of what? Conservation of energy. So we've got 4 joules. And here, guys, everybody look up here. Is it true? We've got this stretched out. We're at this point exactly right here. This point right here. There's 4 joules all stored in the spring. Here, guys, everybody look up here. I'm trying to help you out. Look up here. I'm trying to help. Right. Then you let it go. Now, what's going through the center? Isn't it at this point right here where it's all kinetic energy? But the spring is neither stretched nor compressed at this point. Okay? In fact, every single point along this straight line adds up to 4 joules. For example, here, 2 plus 2 is 4, 3 plus 1 is 4. You guys see that? That's why this graph has to be the shape. It's all conservation of energy. Okay? So you probably wanted to articulate that somehow in a sentence form. Can you guys say? Right? And they were probably looking for that phrase, conservation of energy. When the cart is at plus L and momentarily at rest, a block is dropped on the cart. The block sticks to the cart and the system continues to oscillate. So it was initially just mass m naught, and we dropped on mass 3 m naught, which made the total mass what? 4 m naught. So we effectively quadrupled the mass, right? Just at that point. The frequency of oscillation before was F1, and then after the drop, it's F2. Find the ratio F1 to F2. Right? Did you guys pull up this formula right here? The time period of oscillation for a spring is what? Does anybody remember? 2 pi times what? Square root m on k, right? Well, square root L on g if it's a pendulum, but square root m on k if it's this scenario. Okay, but guys, if you quadruple the mass, which will happen, right? Went from m to 4m, right? Then what has to happen to the time period? Has to double. Now you'd want to maybe write that out, prove that a little bit more, but you guys do see that, right? If you quadruple the m, you're going to double the time period. Okay. Now one more thing. What is frequency compared to time period? 1 over the time period. Okay. So the old time period was some amount of time. The new time period was twice as much time. Here, guys, if you quadruple the mass, quadruple the inertia, it's going to take twice as much time to cycle back and forth. So it's going slower, right? Which means the frequency is less frequency. In fact, it's half as frequent, isn't it? Okay. So I think the new frequency compared to the old frequency should have been 1/2. That should have been your answer. Okay, you guys get there? Right. Again, I would write that out more, but I'm trying to save a little bit of time here. There's more. The dashed line shows kinetic versus potential energy of the block cart spring system after the block is dropped onto the cart. The graph is identical as before. Why should it be the same using physics principles? I might say something like this. I might look at this point where it was completely stretched out and say, well, all the energy was stored in the spring at that point. Then if you effectively quadruple the mass, the energy is still stored in the spring, so still 1/2 kx squared, right? And then, energy is still conserved. So I would definitely mention that phrase again, conservation of energy. Energy is still conserved, right? And in my particular explanation would have to do with like at the point that was dropped, the energy would have to be stored in the spring at that point, but still the same amount of energy, right? Okay. Now, guys, remember too, though, that it's going back and forth slower, right? We didn't slow down the whole system. Now it looks like it's in slow motion. So when it's going through the center, it's going slower, right? Is it still 4 joules of kinetic energy? Yes, it is. Here's kinetic energy. 1/2 mv squared. Guys, it's 4 times the mass, but it's half the speed. Guys, 4 times the mass, half the speed, half squared, isn't that all a wash? It's still the same amount of kinetic energy, which is still going to be 4 joules through the equilibrium point. Are we good? Okay. Finally, after the block is dropped on the cart, consider a system that consists only of the cart and the spring. So even though the block is along for the ride, we're not actually considering the block. I know that's a really weird way to frame that, but okay, we'll run with it. On figure 4, sketch a solid line that shows the kinetic energy of the system that consists only of the cart and spring, but not the block after the block is dropped on the cart. Okay, now this one was definitely a curveball type question. I had to think on this one a little bit, but I know what they're looking for. Right, so we're doing kinetic energy in joules, potential energy, spring potential energy also in joules. It went up to 4 units. 4 units. Okay, 1, 2, 3, 4. Okay, right. Now when the whole thing, when the block was just dropped on the spring, the whole thing was stretched out and all the energy was stored in the spring. So this point's still here. Right, here's the original line. Right, that they dashed, right? That was just the single cart going back and forth by itself, right? But now there's a block on it, and the whole thing is slowed down. In fact, you guys know that through the center, we kind of figured it had to be half the speed, right? Because if it's 4 times the mass, it has to be half the speed, so it's the same kinetic energy initial, right? So if we're now only focused on the cart going through the center, and the spring's not stretched through the equilibrium point, 1/2 squared is 1/4, so that'd be 1/4 of the original energy. That's one way to think it'd be 1 joule, right? So your solid line should look like this. This is exactly what they were looking for. Okay. Another way to think of it is that the whole cart block system itself going through the center, so it would have been 4 joules collectively. 3 of those units would have been with the block, and 1 of those units would have been with the cart, because those were the masses. Okay. Right. So that's exactly what they were looking for. Okay. Right. Any questions there? Right, number 2. Ooh, 12 points, 25 minutes. Students conduct an experiment to determine acceleration of a cart. The cart is released from rest at the top of a ramp. The x-axis is defined to be parallel. Oh, look how they define the x-axis. They already defined it parallel to the ramp. And the positive direction is, well, the way that it would want to accelerate. Okay. The students collect the data as shown. Right, so we got time data and position data. Okay. I'm going to guess this is probably some kind of parabola type relationship. Do you guys think? If you did x versus t, do you think that'd be probably a parabola? Right. I think it should be. There's some version of that. Right. So indicate which quantity should be on which axis to determine the acceleration of the cart. Now, if you're thinking that it's going to follow something to do with this, x is 1/2 at squared. I mean, that's what it would be, right? It's going to be some version of that. Right. Then here's what I would do. I would put the distance, or maybe I'll call this d. Maybe I'll call this, well, I don't know, d, whatever, right? This could be your y-axis. I just don't want to have the letter x on here twice. I would put t squared on the x-axis, right? And then 1/2 a could be the slope, right? Or, let me give you guys an alternate, because usually there's several answers they'll take. Could you slide this 1/2 over to the t squared and do a times 1/2 t squared? Right. Sometimes I did this with you guys too, or some version of this. Right. So this could be your y-axis. Now this could be your x-axis. Right. And the advantage of doing it this way, of embedding that 1/2 into the x-axis, is that the slope is exactly what you're solving for, is exactly a. Versus if you did it this way, you'd have to still like double the slope. But here it is the slope. Right. You guys see that? Right. So I think either one of those would have been really good answers. Yeah.
Is 2 times the distance work?
Yep, you could have done that. You could have done 2 times the distance. And yeah, so you could have gone QD is a times t squared, right? Y-axis, x-axis, slope. Could have done that too. Yeah, that works too. Okay, right, guys got that? So those are 3 great answers. All right, are we good? All right. Then they wanted you to graph that, so you go ahead and do that. It would have worked. It should have lined up in a straight line. Use the line you drew to calculate experimental value of acceleration of the cart. Okay, if you did it this first way, you'd have to double the slope. If you did it either of these other 2 ways, the answer just would be the slope. Okay, right? Students are asked to determine experimental value due to gravity. What additional quantities do they need to measure? Right, I'll give you guys 2 options they could have looked for. You either could have gotten this angle with a protractor, right? Because here, if this angle is close to 0 degrees, it's not going to really accelerate at all. If it's close to 90 degrees, it should be pure free fall. So this angle definitely matters, right? Alternatively, you could have said, well, if I wanted this height change and either length of the ramp or the height change and this horizontal, you could have done some kind of like inverse sine or inverse tangent and effectively also got this angle, right? one or the other. Either you measure this angle with the protractor, or you measure two of these legs of the triangle and you do some kind of inverse trig relationship. Okay, right. So you have to know that. Now write an expression for experimental value of gravity in terms of acceleration. Okay? One of the very first labs I ever had you guys do was basically this. You guys remember rolling those Hot Wheels cars? And you basically did this. You did this. You did like x squared, or sorry, x versus t squared, I should say, right? And it, I had you guys do this version of your lab, one of the very first labs you ever did. Okay? Then you could go the extra step, and you can say, well, I can figure out what the gravity field of the planet is. Now we saved that for unit 2. Like this was a unit 1 lab, kinematic motion. But when we got to unit 2, I said, hey, if you know what this acceleration is, and you know what the angle is, that you can use to figure out the gravity of the planet, or vice versa, right? Like once you have so much information, you can kind of figure out everything. If you know the gravity field of the planet, you can figure out the predicted acceleration. Let's throw in an angle of theta right here, right? Let's do a free body diagram, and I'll show you guys exactly how to get this, right? We've done this many times. We did this many times, right? I got the weight of the object here. I got the normal force here, call it F sub n, right? And there should be no frictional force. That's it. There's only 2 forces, okay? There's no friction, okay? This weight you can break into components, right? Notice I'm holding my ruler parallel to the surface. You guys see that? So this is still theta, it's the same theta. Here's your mg cosine theta, which exactly cancels out with the normal force. But here is the one you're interested in. Here's mg sine theta, right? The sine component of the weight, and that is the net force. Okay, so I would say F net is mg sine theta. Isn't that true? Isn't that true? Right? Right. Now, F net, Newton's second law of motion, is that m times a equals mg sine theta? Is that true? Right? Does the mass of the cart cancel out both sides? Right? And then finally, now, usually that's where I got you guys. The acceleration of the cart should be this in terms of the gravity of the planet. They want you to go one more step and say, well, what is the gravity of the planet if you did this whole experiment? Let's say you're hopping planets and like, I'm on Mars. What's the gravity of the planet, right? Okay. This is the answer they were looking for. Take the experimental value of acceleration, which is either the slope of the graph that you made or double the slope, depending on how you did it. Okay. Divide by sine of that angle. That's exactly what they were looking for. Okay. Right. Okay. So if you wrote that, there you go. Guys, this was worth 12 points. If you didn't get all the way there, but you got some of these steps, you probably picked up some points along the way. Okay. But if you got all the way there, then I bet you got all those points. Unless there's more. There is more to this. The students calculate the experimental value of acceleration due to gravity to be significantly lower than 9.8 meters per second squared. Okay, so we are on Earth. We were looking for it to be 9.8 meters per second squared. Okay. What is a physical reason other than friction or air resistance that could lead to significant difference? Right. So, because that would be the most obvious thing, right? Some kind of frictional loss. But they're saying, okay, well, besides that, suppose there is no frictional loss, or you can account for that, or okay. So do you guys remember here? I'm just gonna mention a name here. I recommended when you guys were reviewing a guy on YouTube called Alan Sao. He's on YouTube. He also has solutions for all these. I double checked. So I was getting pretty much what he got. Now this one, he did something a little bit different than I would have. So I'll just let you guys know. He was saying, because he was struggling. He's saying, well, what could that be? He said, well, maybe this angle was mismeasured. Okay, that could possibly be true. He would say maybe there's some other kind of external force, although I don't think that's really what they were looking for. Because I think I do know what they were looking for. I think I do know. Does anybody have a good guess on what would cause the experimental value of acceleration to be lower than what they predicted? Who has a good guess? Okay, I think what it was. I think what they were looking for. I think like their golden answer. Oh yeah, go ahead. Okay, so it's not normal force. That's still a wash. Okay. I think what they were looking for was the rotational inertia of the wheels. The fact that there's wheels here, right? Because usually how they pitch this question is they say that it's just a block on a frictionless surface. They didn't technically do that. In your guys' Hot Wheels cars, well, the wheels were so small they would have hardly any rotational inertia. I think they were looking for rotational inertia of the wheels, which would slow the system down, right? Now energy would still be conserved, right? If you had another hill, it would still roll up at the same height, but that would do that. explain how the physical reason you can identify it in part CI would lead to decreased experimental value. Okay, because the full conservation of energy equation would now not look like mgh equals 1/2 mv squared. It would look something more like this: mgh equals 1/2 mv squared plus 1/2 I omega squared. And if you had, whoops, let me back up a little bit here, right? And if this was like for each individual wheel, you could say there'd be 4 wheels and it'd be something like this. Okay, so this would be okay, then this V would be less. Now, if this V and this omega are connected, you could say, well, V is equal to omega R or some version of that, raise the wheel, right? But still, the V would be less than expected. It would slow the system down, right? It would do exactly this. It would show too low gravity. On the following, students want to confirm acceleration is the same whether the cart rolls up or down the ramp, which would be true. They could have asked that. They said, would it be the same? But the answer would be yes, right? It doesn't matter which direction the cart's moving. The net force and the acceleration should be the same. Right? On these graphs, draw, whoops, sorry, more details. They start the cart at the bottom. They push the cart up the ramp. These little streak marks show the direction of motion going up the ramp. Momentarily comes to rest, and it's going to roll back down. The positive direction is still down, so they push it in the negative direction. You guys see that? Okay. On the following graphs, X versus T and V versus T during that scenario. Okay. I know exactly what they're looking for, so let's get these on the board. Right. X versus T, V versus T, and they gave you actually they didn't write units, but you could guess the units would be like meters and seconds and meters per second and seconds. Okay. Right. So the fact that they push it in the negative direction and it's going to follow a parabola shape, they were looking for something like that, right? Or maybe it touched the axis, or maybe even had to go below the axis. Any of those would have been okay. Right. For V versus T, a couple ways you can think of it. The fact that they pushed it initially in the negative direction, it came to 0 and turned around in the positive direction, and the acceleration was constant the entire time. They were looking for something like this, right? Alternatively, you could say like the slopes of these, right? So start out with a steep slope, and then shallower slope, and then 0 slope, and then shallow positive, and then steep positive, right? Right, you guys see that? Right, are we good? Yeah. Okay, because that has nothing to, okay, because this normal force canceling out this component of its weight has nothing to do with the motion of the cart, right? It all cancels out in that direction. The only thing that's driving the motion of the cart that's providing kind of net force is forces that are parallel, right? They said there's no friction. If there was friction, you could say, well, maybe friction has something to do with like some like factor of the normal force. Is normally how we do it, right? Even if there's friction with the wheels, that doesn't count either, right? This is not driving these two are always balanced out, so they're not driving the motion.
That's what I'm saying. Is there not a component of gravity that's canceled out from the normal force and a component of gravity that's perpendicular? Sorry, the perpendicular that's canceled out and parallel that's not, and that's what's driving it.
Okay, this one here is the only component driving the motion.
Right,
that's it.
That's what I'm saying. A part of gravity is canceled out from the normal force. Mg cosine theta is canceled out.
Yeah, these two are canceled out.
So instead, only mg sine theta would be driving the motion, which
Yes.
is smaller than gravity.
Yeah,
Right. So
but
yeah.
here, but remember, okay, yeah, guys, this will not go pure free fall down the ramp, but that's not what they're looking for. They want you to come up with this expression here. They said you're gonna figure out what an A is based on kinematic motion, the X and the T. They gave you a table, right? So something to do with like the slope of X versus T squared, so something to do with that, or maybe 2X versus T squared, right? You can get the acceleration. Then if you divide that by the sine of this angle, you should get gravity field of the planet, and it should be 9.8 meters per second squared, right? Let's say you do all that, and it comes out to like 7 meters per second squared. You're like, what? 7 meters per second squared? It should have been 9.8 meters per second squared, right? Well, if this is too small, then something else is wrong, right? And one possibility is maybe you mismeasure the angle. But there has to be, but if your angle is fine, if your angle is measured fine, then it's something to do with this acceleration. And this acceleration has nothing to do with this or this. It's only this. Okay, so it could be the rotational inertia of the wheels is probably like almost certainly what they were looking for.
Oh, but Mr. Griffith, is it talking about the acceleration of the cart is less than g expected, or is it talking about the g expected solved from
G expected solved from this is less than 9.8 meters per second squared. Yeah, that's what it's saying. Okay. All right. Okay. And so everybody good so far? Okay. All right. Number 3. Oh, it's the other 12-pointer. All right, so we got a rod, a spring, and a block. Small block, mass m naught, attached to a spring with spring constant k naught, attached to a rod on a horizontal table. The rod is attached to a motor, so you can rotate at various speeds. When the rod is not rotating, the block is at rest. Unstretched length L, so L is unstretched. All frictional forces are negligible. Okay. At time t1, the rod is spinning, so the block moves in a circular path. Okay. Constant tangential speed v1. At distance d1, so d1 is the stretch. Okay. At time t2, we got stretch d2, and d2 is greater than d1. Right? Okay, so you guys remember that setup? All right, let's see what they're asking about. On the dots, draw the force exerted on the block by the spring at those times. The force should be okay. So we're doing a free body diagram on the block. Well, we're ignoring the weight and the normal force. Right? So I would do something like this. Right. So here's at T1. Here's at T2. Right. At T1, it's going to do something like this. At T2, it's going to do something like this. And what they were looking for was that this should be greater than this. Okay. Right. Right. Referencing D1, D2, describe reasoning for the drawing arrows the length that you did. Right. So basically, why would this be greater than this? I might say that you have to spin it faster for it to like stretch more, and maybe something to do with centripetal force. I might bring in an equation like centripetal force, which in this case would be provided by the spring, okay, is equal to mv squared on r, right? Of course, you guys know that spring is going to be k not d, so some version of that, right? Okay, this is going to enter in at some point, okay? Okay, so you're spinning it faster, so the spring force is going to go up because centripetal force has to go up. Okay, is the tangential speed in v1 at time t1 greater than, equal to, or less than v2 at t2? Right. Well, guys, if it's stretching more in figure 2, it has to be spinning faster at t2. It's spinning faster at t2. The spring force is greater in version 2, figure 2. So I'm going to go with v2 is greater than v1. Right, guys said that v2 is greater than v1. Hopefully everybody got that. Right. Justify your answer without using equations. See, I would be really tempted to bring in something like this, but I think we're going to say that for a later bit. Okay. So yeah, without equations is tricky because, in physics, it's always nice to have an equation to back up and say, like, here, this is exactly why I think, but it's my justification. But maybe if you could just say something to do with, well, if it has to be, if it's spinning faster, then that would stretch it more. It would require like more force. It's some version of that. Okay. Okay. So they just want you to write that out in sense form. Okay. Now I think we're going to back this up with equations, and then they're going to say, does your equation match your justification back to the earlier part that we just covered? Okay. That's usually how this goes. Consider a scenario where the block travels in a circular path where spring is stretched distance d, unstretched length L. Determine an expression for the magnitude of the net force on the block. Express your answer in terms of MKLD and any fundamental constants as appropriate. Okay, so the net force on the block. The net force on the block is the spring force, which is this right here. This, guys, this was all they were looking for. I had to think about this one a little bit, but notice they didn't say anything about V, right? And L is the unstretched length, so L is not part of the spring force. And M is the mass of the block. Maybe you could bring that in with the centripetal part. This is all they were looking for. They just wanted to write K not D, right? That may have been one of those that was like, so something you may have just overthought it if you missed that. Okay, that's all they were looking for. The spring force, which is the net force, is spring constant times the stretch distance. That's it. That's it. Okay, that's all they were looking for. Derive an equation for the tangential speed of the block. Express your answer in terms of, well, those same values, MKLD. Okay, now here's where we get to set this equal to this. Okay, the spring force was providing centripetal force, and now we get to solve for this V right here. Right? Okay, so where's that? Now I do need to make one more substitution. You guys see this R right here? You guys see this R? Let's go back to the diagram. Isn't the radius of curvature actually L plus D. You guys see that? L plus D, right? Either way, right? It's L plus D, right? Okay, so I do have to make that substitution. So let me go and do that. I'm gonna say MV, which we're solving for, squared on R, but instead of R, I'm gonna say L plus D. Okay, and that's equal to KD. Okay. So there's the stretch force of the spring. This is a force, this is a force. So triple the force is provided by the spring force. Okay. Here, I just put this here and this here, but let's swap this up. But you guys see that, right? Okay, so we're solving for V. Few algebra steps. Cross multiply this L plus D, divide the M down. So V squared is equal to K naught D L plus D. This is all divided by M, and then take the square root. V is the square root of all that. K naught D L plus D, all divided by M. Okay. Okay. I think that's exactly what they were looking for right there. Okay. Well, let me check the units. Let me make sure the units work. Guys, K, is that newtons per meter? K is units per meter, right? Which is like kilogram, meter squared, per second is a newton, and then per meter. So divided by meters. D and L plus D, those are meters and meters. So got meters and meters. And then divide by mass, which is in hold on. Kilograms. Oh, whoops. Kilogram. I'm so sorry. I messed up my sorry. I messed up my units. Okay, Newton per meter is spring constant. Distance is in meters. L plus D is also in meters. Mass is in kilograms. And this whole thing is square rooted. Okay, I messed this up. Whoops. Okay, so we got that right. Meters and meters is going to cancel. Guys, Newton. What is Newton per kilogram? Isn't that meter per second squared? Okay, so you got square root of meter per second squared, because 1 Newton is 1 kilogram meter per second squared. F equals MA, right? For that. Okay, and then I got meters right here. Guys, what's the square root of meter squared per second squared? Meters per second, which describes the speed, so we're all good. Okay, right. There's a little extra check right there. Okay, all right, are we good? All right. Oh, there's more. Right. Consider a scenario where the block travels in a circular path. The spring is stretched distance D from unstretched length L. Wait a minute, did we just do this? Oh, okay. Sorry. Yeah. Sorry, we just did this. We just did this. I guess I flipped this packet. Does your equation for tangential speed of the block? So we just came with the equation. Agree with your reasoning for part A. Remember, back in part A, we're saying V2 had to be greater than V1 if it was stretched more. Right. Now we have an equation that could possibly back that up. Right. Ooh. Well, K for the spring is the same. The mass of the block is the same. The unstretched length of the spring is the same. But do you guys see if you're increasing that distance D, that you're also increasing the V? So that's what they're looking for. They want to say, hey, if this D is increasing, this V must also be increasing, right? Right. Now you have an equation point 2. Check yes, and then write something like that. Okay. All right. All good. Good. All right. Number 4. Back to 7-pointer. A block of unknown mass attached to a long, lightweight string, wrapped several times around a pulley, horizontal axis through its center is shown. Uniform solid disk mass M, radius R. Rotational inertia is 1/2 mr squared, which is true. Now, they would have to give that to you. They did. So rotational inertia is 1/2 mr squared. The pulley can rotate without friction. The string does not slip when the block falls. When the block is released from rest and it travels toward the ground, the magnitude of the tension is F sub T, which should be a little bit less than the weight of the block, right? Okay. Remember that the weight of the block is a little bit more than the tension so that it can overall accelerate down. Okay. Maybe accelerate slowly, but still accelerating. Determine the expression of the magnitude of angular acceleration of the disk as the block travels downward. Express your answer in terms of all those things. There's a couple ways I think you could go about this. You could go about this in terms of conservation of energy, or you could go about this in terms of torque. Now, I think the faster way to do this actually would be conservation of energy, or sorry, torque. But let me try that. So, alpha for the disk. Right. is it true torque is equal to R cross F, but torque is also equal to I times alpha? Is that true? Right, and we want to solve for alpha, so I'll say I times alpha that we're solving for is equal to R cross F. Isn't that true? Just like that. Okay. Now this I is your 1/2 mr squared. Right. The radius is still the radius. So this radius is the same. Okay, that's why. Okay, so that, and the force is actually the tension force, which again is a little bit less than the weight of the block, but they went ahead and told you to solve it in terms of that. Okay. Is that? So we're solving for this alpha. One of the radial value goes away. I'm going to say alpha is, okay, I got a tension force here. I got a 2 here. Okay, and then I'm going to divide by M and R. This should be what we're looking for. Okay, you guys see that? Right, not the only way to solve that. I think that's the fastest way to solve that. Probably what they were looking for. Okay. Again, if you didn't solve this whole thing, but maybe got like these 2 first lines, you may have picked up a couple of points along the way. Okay, but hopefully you got the whole thing. Scenarios 1 and 2 show 2 different pulleys. Scenario 1, it's a solid disk, just like we were looking at in part A. Scenario 2, it's the same mass and radius, but now it's a hoop. So I bet the rotational inertia is closer to just pure mr squared. So maybe 1/2 mr squared on the left, and closer to mr squared on the right. Each pulley has a lightweight string wrapped around each pulley. Free rotate, negligible friction. Both scenarios, they begin at rest. Constant force FA for time interval delta t. Wait, what is that A? What is that?
Yeah, that's a
Okay. Right. Oh, okay, yeah, F sub A. For the same time interval delta t, causing the pulleys to rotate without slipping. After time interval delta t, the change in angular momentum of the disk is equal to the change in angular momentum of the hoop, but not true for rotational kinetic energy. Consider scenarios 1, 2, and a time interval delta t, and coherent paragraph length response that may contain equations and drawings. Explain why the change in angular momentum of both is the same, but kinetic energy is not. Okay, there might be different answers they would take for this. Let me start with why the change in angular momentum would be the same. You guys remember change in angular momentum is torque times time interval? Yeah, you guys remember that? Torque times time interval? Great. And torque is the same for both. It's the same radius, and it's the same tension force, and the time interval is the same. So the angular momentum has to be the same, but with the change in angular momentum has to be the same. And if they both start from rest, then final angular momentum is the same too. Okay, now you'd have to write that down in paragraph form, but I would have this equation for sure, right? If you have this equation, I bet that's really what they were looking for. Okay, I bet that was somewhere in there the grading, right? Or maybe you just explained that out in words. Okay? But why would kinetic energy not be the same? Okay. All right, so kinetic energy, let's think about this. I might, there might be different ways to go about this, but I might do something like this. M of the block, hold on a minute. I want to do that. Block times gravity times the height change. Here, let me play around with this a little bit, and then if I'm not liking it this way, I might try something else. Right. Is 1/2 m block. No, remember they never gave you the mass of the block, right? Times the speed of the block squared plus 1/2 I omega squared. Now this B and this omega are connected because that string's tied around the axis of this guy. Right? But remember, it's 2 different I values, right? 2 different I values. Okay. They say the rotational kinetic energy is always greater for the disk. Rotational kinetic energy always greater for the disk. Okay. Here, let's take bird's eye view here. Now this would be the same for both. Okay, but the disk has a smaller rotational inertia, right? So, you know what? Let me try this a different way. I pause this a moment. Right. I know.